Okay, so we've looked at radioactive decay as in alpha, beta, gamma, but now we're going to look at it as a whole process of a large sample of radioactive nuclei decaying. And so we're really going to be thinking about half-life and activity of isotopes, and work out how we can calculate the activity of an isotope and interpret some graphs and numerical data of our radioactive decay. So what is radioactive decay? Well, we know from what we've thought about before, it's all about unstable isotopes changing into stable isotopes, and we know it's random. And we've got one element changing into another element if we've got alpha and beta happening, and ionizing radiation being emitted in all cases, and sometimes we've just got gamma being emitted after the fact. But what is half-life? Well, if we imagine time 0 and having a set number of nuclei n, all the red ones there are unstable. After one half-life, half of them will have decayed to white. After two half-lives, half of those will have decayed, so we've now got n divided by 4. After another half-life, we've got n divided by 8. So we're decreasing by half the number of nuclei we started at the beginning of the time period to the end of the time period. So one half-life means we've decreased by 1/2. Two half-lives means we've decreased by 1/2 and then half again. Okay, and so on and so forth. In theory, we never get to 0. Okay, so if we're thinking about a definition, the half-life of a radioactive isotope is the time taken for the mass of the isotope to decrease to half its initial mass. That is really difficult to measure. How can we separate all those masses out? So we've got other definitions which are coming up in a second. If a half-life is very long, then a substance will remain radioactive for a very long time, to the point where it can be dangerous and difficult to manage. If the half-life is very short, it can decay quickly, which can be useful because it's not harmful, but it can be useless if we want to use it for something. But what about this activity? I talked about activity at the beginning. Well, the activity of a radioactive isotope is the number of nuclei that are disintegrating per second. So how many nuclei disintegrated per second, number of decays per time, and it's measured in becquerels, which is decays per second. So it's almost like a frequency. Okay, so activity is the decays per second. So if we say, what's the activity of that sample? We want its decays per second. However, as we go a bit further on, we'll realise that actually activity itself is really difficult to measure. So we've thought about a half-life with the mass, but how do you separate all those masses? You can't separate the non-decayed from the decayed. So let's think about half-life now as the time it takes for the activity of a radioactive sample to decrease by 50%. That's another way of saying a half. So we've got another way of writing our definition of half-life using activity. Or we can have another definition of half-life including count rate. And that is the most useful of all because we have Geiger counters and we can actually count rate, whereas we can't count activity because it's difficult to count disintegrations of a whole thing per second. And we can't count mass because we can't separate it out. So the most common useful way of describing half-life is using count rate. Okay, here are some questions to have a go at. You read them through, you pause this video and you have a go at the questions. Answers. Right, so there are the answers. Have a look at some of these, the answers to the first question. Answer the second question. Answer the third question. Hope you didn't just rush through and look at the answers. Dice versus number of throws, or log of the number of dice remaining against number of throws. So do it, and you'll find you've got two graphs. I'm going to move on to the graphs now, so you might want to pause until you've done your graphs. Okay, so if we plotted the first graph, we would find we would end up with this curve that is going down from 1 to almost nothing, and that's showing us that the parent there, the original unstable nuclei, is getting less and less and less. We could plot a decay curve with the number of stable nuclei appearing, and that is the inverse. But you notice we've got exponential curves here, and we can, if we imagine we've got 100% or a whole amount, and then we've got half the amount, we can read off our time in half-lives from this graph. We'll come back to doing a bit more of this when we do some questions. Okay, now we probably already knew that was going to happen, but I've asked you to plot that second graph. Okay, so if you're plotting that second graph, actually we are plotting the exponential relationship, and here is the exponential relationship between number of original nuclei, the number we've got left, and something called a decay constant, and t time. So in this equation, n is the number of nuclei we've got any particular time t, n0 is the original number of nuclei, and then we've got this something called the decay constant, which we'll look at in a few seconds, minutes, days, weeks. Right, so I asked you to plot that graph of log n versus t, and you'll have a straight line with a gradient, and that gradient will be the same as this thing called with the decay constant, and the intercept of that gradient should be the log of our original number of nuclei. Now I'm really interested if you've seen that. Now we can actually come up with some sort of relationship from that graph. We can show that the half-life can be given by the equation ln2 divided by our decay constant. Now, how can we see that equation there? I'm looking here for just the gradient. I'm just looking for the gradient because I'm just looking for the gradient there, which is this thing called a decay constant. Okay, now what is a decay constant? It's unique to isotopes. It's a probability constant. It's the probability of an individual nucleus decaying per second. It's got a symbol lambda, just like wavelength, nothing to do with the wavelength, stupid people in physics. So it's got the same symbol, but it's not to do with wavelength, ignore that. And it has the units of frequency per second, or you could even think about hertz, but we don't, we just go per second. However, that could be like a multiple choice question, couldn't it? What also has the same units as frequency? Well, decay constant. Okay, so where's this all come from? Well, it's come from the idea of having very, very small amounts, okay, and ratios, and the idea that we've got rates of change. So if we start with a sample of material with n number of nuclei, as it's decaying, it's changing by changing the amount of nuclei it's got remaining by a fraction. That fraction we're going to call delta n, and that's happening in a fraction of time, which we're going to call delta t. And this, we've already said, it's a proportionality constant. Okay, so the rate of change is proportional to this constant times the number of nuclei that we had to begin with. Okay, now, but we've already said back ago that the activity is the rate of decay of nuclei. Okay, so dn by dt is A. So then we get a new equation which is saying the activity of the sample A equals lambda n. Another equation. And then we come up with these 4 equations that talk about the original definition of half-life. Okay, so these are 4 equations. You don't get 4 of them in the datasheet, you just get one of them in the datasheet. I think it's the n. So we can think of radioactive samples decreasing, and we can measure them in 4 ways. However, we can only actually measure them in inverted commas in one way meaningfully. So this exponential decay rate is related to either the original number of nuclei, the top equation, the activity of the nuclei, the second equation, count rate, the thing we actually can measure as an exponential equation, or mass. And again, you think you can measure the mass, but you can't measure the mass. Okay, so the one that we're going to be using a lot in practical work is going to be the count rate changing exponentially. However, theoretically, in calculations, you might end up looking at the other equations. But you only need to remember the one. And in fact, you don't even need to remember it because it's in the data sheet. Okay, and that's where I'm going to stop. So what I'm going to get you to do is have a go at a few questions using all of this.